Okay, I end this chapter on dielectric with two quick examples. This is to be dielectric bodies that we put in external field. Lecture 5B2. So let's take a problem example that a uniform, homogeneous linear dielectric sphere of radius r and dielectric constant K1 is placed in an external field which is E equal E naught K in the Z direction. To generalize the problem, uh, let us assume the medium outside has a dielectric constant K2. Find the dipole moment induced in the dielectric sphere. Normally, in most of the problems, one could have taken this K2 to be air and that will be 1. Okay, but to generalize, I have taken it to K2. So the situation is that we have a sphere of radius r and it is put in a uniform field of E naught K. E naught K, and inside is K1, the electric constant, okay, a relative permittivity of K1 and is K2, radius r. So the question is find the dipole moment induced in the dielectric sphere. This is a linear homogeneous dielectric sphere. It's a very instructive problem of the use of boundary condition. Now the strategy is first use boundary conditions to obtain bound charge densities and use it to find E and P. In many problems you have seen, I have done the other way around. Okay, that is find somehow B, then go to E and then go to P. There is no D here. All right. So this is a dielectric and put in an external field. So I cannot use that strategy. So I reverse the strategy and say that I'll try and find out the bound charge first, and from there to P, and then there to E. All right. So that is the illustration. So let us make an assumption, which you can test later, that we expect the field and polarization in the dielectric sphere to be uniform. And hence, we look for sigma b at the surface and rho b is equal to 0. Since it is a linear homogeneous dielectric and there is no embedded free charge in it, so rho b would be 0. So all we need to do is to find out sigma b at the surface, okay, uh, and then from there go on to find out what is the field and what is the polarization. Okay, but crucial assumption is that the field is uniform. Nothing has told me that it will be uniform, but I expect, and if it turns out to be that way, then I'll be lucky. Okay, so let the field inside be E1 and outside be E2 after placing the sphere in the external field. Let's just say that E1 inside and E2, E naught K has already been outside. Now, in absence of any free charges, I know that there are no free charges, and hence I can say that the normal of the normal D11 must be equal to D2n because there is no free charges. Okay, so if I now, but I know E1 and E2, so I should be able to translate this in terms of E1 and E2. That is K1, E1 is inside, E1 dot n is of course R hat in this problem, and K2 is E2 dot En. So I am using this boundary condition to write this as my first equation. Okay, and now I can also write that E2 dot n, okay, if there is some sigma b at the interface, then the E2 dot n must be because it must be suffering a jump of sigma b by epsilon naught. So E2 dot n must be sigma by epsilon naught plus U1n as I'm going out. So that is my second condition. Now I can, this is 1 and this is 2, and hence I can now write down that K1 E1 dot n from here is, I replace, okay, K2 and by E2, okay, so K2 and E2 dot n E2 dot n is nothing but this quantity. So I replace that from 2. Okay. So, and then now I have equation in terms of E1, and I can solve for sigma B. So sigma B turns out to be, I just solving this, okay, bringing sigma B, and then turns out to be epsilon naught K1 minus K2 U1 dot n. Okay, I just brought this and took sigma B out in that case. But sigma B, we know, must be equal to P dot n. And hence, I know what is P. Now, sigma B is equal to P dot n, and I have already using boundary conditions obtained sigma B in terms of E1 dot n, and hence, I know P. P must be this quantity depending on E1. Okay, so I write down my P is epsilon naught K1 minus K2 by K2 E1. So once I know P, okay, I first thing, let's note that is consistent with the assumption of constant field and polarization. So polarization is constant, okay? And let's work out, okay? So, but E1 is equal to, we know, inside is E naught minus P by 3 epsilon naught is due to E naught, and this field polarization, since I know P, I can find out what is the field inside because of the polarized sphere, and I know polarization, and that is E naught minus P 3 by epsilon naught. We have done that enough number of times. So let's calculate that. So let's put that in, and that is from here, if I put this in P, and then E naught minus K1 minus K2 by 3 K2 E1. I just plug this P into this. So that tells me that E1 is 3 K2 by K1 plus 2 K2 E naught. So I've gotten E1 in terms of E naught. Basically, I first solve for P from sigma B and plug this in to get E1. E1 is inside. E naught is the applied electric field. And hence, now I can obtain the total P. I can write down P in terms of, earlier P is written down in terms of E1, but finally I want to get P in terms of E naught. So I got now E1 from E naught, and hence I can now write this down. K2, K2 cancels, and this is 3 K1 minus K2, K1 plus 2 K2 E naught. So finally, first I get P in terms of E1, and now P in terms of E naught. All right. So now there can be two cases. Either K1 is greater than K2, okay, then the P that will be induced will be along E naught in K direction. If K1 is less than K2, okay, then the P induced opposite to E naught. Suppose K2 is air. Okay, there is no, the medium is vacuum, and there is no dielectric. Then of course K1 would be greater than K2, and then there will be a dipole moment induced along this direction. Okay, and then what will be the total dipole moment? Of course, this is the P would be this polarization and this uniform polarization, and hence the total dipole moment will be simply the 4 pi by 3 r cube by P. Okay, so in each case, okay, this will be true, and I would ask you as a task to use this and carefully plot the field lines for both these cases, both the cases when K1 is greater than K2 and K1 is less than K2. Now we solve the problem. This problem is solved in many ways, and even very rigorously by using special techniques of maths. But the clever use of the boundary condition can actually lead you to a simple solution. That was the demonstration that I wanted to do. Okay. Now let me take up the similar problem, same problem almost in another form. Okay. That is, uh, it is now the approach is called the successive approximation series approach. It's the same thing, that I uniform homogeneous linear dielectric sphere of radius r, and now instead of K1 and K2, I'm saying, and susceptibility chi e is placed in an external field of E similar. Now, let me restrict myself to say that what is the new field inside the sphere? What I want to demonstrate is good enough for my a new field inside the sphere. Okay. This is another approach to obtain the field inside. Um, so is the same. This is E naught K in this direction and a uniform dielectric sphere and is chi E. Now, so strategy now is iterate the process of updating the polarization and the field and see if it converges. What do I mean? That is initially I get E1, so E naught, and let's consider the field to be E naught. Then it will polarize to, let's say, P1 or P naught, and that P naught will produce an electric field. And then I'll calculate the new electric field, and then I calculate the P1 from there and P2. Okay, so every time I keep updating the field and find out the polarization, and then use that polarization back into the field and see if this process converges. That is the strategy. So let's see. So E1, there's the first step. Okay, is we know that this inside I am worrying about minus P naught by 3 epsilon naught, and that is nothing but chi by 3 E naught. Okay, let me just put that in, and then now according to the new E1 I have obtained, so from E naught I have obtained E1. Okay, because of the first level of polarization. Now I update the polarization as by replacing E1. Okay, so then I would say P1 at the next level would be now chi naught. Okay, chi E and E1. So E1 I have already gotten minus chi E3 by E naught. So I got P1. Now I know P1, I can calculate E2. Okay, so E2 will be again minus P1 by 3 epsilon naught. And we can clearly see that all we have done is multiply minus chi by 3 into here, the square. I can keep doing this process. So from E2, I'll calculate P2, and from P2, I'll calculate E3, and so on and so forth. And it is clear that what will happen. So at the nth step, okay, I would have minus susceptibility by 3 to the power n E naught. And now I have done these steps every time I modified. So what I'll need is a full summation of the series. Okay, so chi minus chi by 3 to the power n E naught. Every time I've gotten in terms of E naught, the nth power. And I simply sum that. This is simply a geometric series. And I know how to write a geometric series. Okay, and hence E inside, okay, because of this series, many steps that I've taken is simply 1 by 1 plus chi by 3 E naught. All right. So this is the process of successive approximation. But what is the guarantee that I've gotten the right solution? Okay, let's check. Okay. So first thing, it is also important again to check that E in is actually, it is just a constant and hence is uniform field. That's crucial actually. Okay. So let's check the answer for if their consistency. That is, if I've got an electric field, it should produce me the right polarization, and that polarization should give me right field. Okay, if that consistency is there, then my solution is all right. So I can calculate from on this basis E in the polarization epsilon naught chi E in I just simply plug in here, and that is my polarization. So does this polarization give you this electric field? Okay. So let me calculate on this basis what is the E due to the sphere is minus P by 3 epsilon naught, and hence it is simply minus chi E by 3 plus chi E. Okay. So, and then I have the total electric field E naught plus E sphere, that is E naught and minus due to the sphere alone. Okay. And then I add that, and that indeed gives me the electric field that I have gotten back here, 1 by 1 plus chi E by 3 E naught. All right. So this is actually consistent. Simple, but it's consistent. Okay. So, but I'll make two comments here. The first comment is, since we applied a geometric series, it should be valid for only for chi E less than 3. But the result is not limited to any such constraint, as it is obtained by other methods as well. In fact, just the method that I showed you in the last example, or even more rigorous mathematics. Also, remember the method worked because the assumption that the field is uniform inside remained valid throughout the process. Okay, so each time the process was that saying that each step the polarization was uniform, and that has been crucial to the success of the method. Actually, for ellipsoids, this happens, okay, of which sphere and infinite cylinders are special cases, that the uniform polarization leads to uniform field inside. So in that sense, you are lucky that in this problem you could use it. Okay, of course, I'm also saying that one can use it for infinite cylinders. All right, so you may like to work that out. So with that, we have come to the end of the dielectric chapter, and you should be now able to work out all the problems given in the home assignment and the practice problem, um, and the practice problem. Okay, so let me